In this short video, we're going to model a fiber taper in FIMMPROP using the EME method. So what we have open right now is a model that's based on the SMF28, which is being tapered down and then tapered back up symmetrically over a length of around 1,100 microns. If I switch over to the symbolic view, you'll notice that the second half of this taper is grayed out. This is what's called a reference section. Because I know it's identical to this, just flipped around, I've told FIMMPROP this, and we only need to calculate one half of the structure, and then those results will be reused for the second half here. So just for efficiency, that is a very valuable setting to have. And then to start the calculation, I'm going to click the button for the scattering matrix, and the calculation has started. For the simulation of continuously varying structures such as tapers, FIMMPROP will automatically discretize the structure. And if you want to view the discretization as it's in progress, we click this button here. And you can see here the discretization of the left side only has started. And if I refresh, you can see here the progress that's being made. And after a couple of minutes, the scattering matrix is displayed, showing that we have about 69% of power transmitting in the fundamental mode at the right-hand side, and the rest of the power is distributed among the cladding modes. And just a final check to look at the discretization. You can see here the fine discretization, which you have control over, but notice that it's done in an automated way where the modes don't change so rapidly at the wider regions, so there's a relatively coarse discretization that's required here, and then a finer discretization on the other pieces of the taper. A couple of things we can do quite easily is view the Z profiles. One thing that's quite valuable is to understand the mode coupling inside the taper as it changes. This is very valuable for understanding adiabatic behavior or design of tapered structures. So if I plot the power of all 10 modes as a function of Z, you can see here that there's certainly a lot of coupling between the modes inside the taper. And this shows you the value of using an algorithm such as EME instead of BPM or FDTD. You don't have access to this information, at least not easily. But you can see here the fundamental mode in blue starts to couple to predominantly, I guess, the green and the red ones, which is the second mode. The green is the second mode. And I'm just flipping through the series, and the red one is the third mode. You know, certainly in the central region as we get really thin, so between 200 and 800. So from here to say here, this central region is really where things change quite quickly. We can also do things such as plotting the mode data, so effective indices of the modes. So again, you can see how quickly the effective index of all the modes change in this central region as well. So you could take this information and decide that you can get to a certain width quite quickly, but maybe in the central region we want to expand it, stretch it out a little bit longer to if our purpose is adiabatic behavior, for example. And then, for example, we could study the transmission as a function of length by using the FIMMPROP scanner. So to set this up, let's create a variable. So I'll add a variables node. And I'll create a variable called L for length. Give it a value of 500. And then in the taper section, replace the numerical value with the variable itself. And now we're ready to do a scan. So let's add a FIMMPROP scanner. Select the fiber taper device that we're going to analyze. And we're going to vary the variable we just created, L, 50 calculations, and we're going to choose a much larger values. So let's go from 10 millimeters to 25 millimeters. 50 calculations, scan, start. And we'll just look at the power in the fundamental mode at the right-hand side. And we'll click OK. Now, the first calculation we did took about a couple of minutes to calculate all the modes along this fiber taper structure. But now we're doing 50 calculations, and it seems to be maybe a couple of seconds per data point, which is a much faster way to do this. Again, this shows the value of the EME method that's employed in FIMMPROP. Quite simply, it's reusing all of the previous data and just updating the scattering matrices as the lengths of each discretized section changes. So we can get a much faster calculation this way. And perhaps I didn't do enough data points, but you can certainly see the trend as we go from 10 millimeters to 25, and the oscillations in the power fade away as we get to the higher values. So you could potentially argue that at around 25 millimeters is around about adiabatic behavior in this case.